Hello everyone, I am Srimanti and I am currently working as an ML engineer. Today I'll be talking about the derivation and maths behind multiple linear regression, which is the second algorithm in this series. I've already covered simple linear regression before in one of my videos, and so today it's going to get a little bit more involved. So without any further ado, let's start. So the first thing that comes is, what is the dataset? So the dataset looks something like this. We'll have like around n features, and we'll have m data points. So these all xi's, x1, x2, x3, xn, these are all n features. And y is our target variable. So total we have m data points. So this is very important to understand. Total we have m data points. And we have n features. Total we have m data points and n features. So our x matrix, so we know that we are given x, we try to find y. So our x matrix will be m cross n. M being the number of data points and n being the number of features. And y is m cross 1, as we know, just a single value. This is y and this is x. Okay, so now we have the data set. We understand what the data set looks like. Okay, so now we have the data set. Now we want to find out the curve. What curve will satisfy our multiple linear regression problem? So basically, in simple linear regression, we know that since we have one x and one y, and it's linear, so y would be mx plus c or ax plus b, some linear function of x. So now, in case of multiple linear regression, we'll be having like x1, x2, xn, n features. So y would be a linear combination of these n features along with a bias. Okay, so what does it look like? Y would be theta 1 x1, theta 2 x2, theta n xn plus theta 0, which is our bias. We cannot use A, B, C right now here because otherwise it will be difficult to formulate the expression and the loss. So remember this is the curve. So let's visualize it. It's very difficult to understand without visualization. So let's visualize it. So, so suppose we have just two. We already saw what it looks like when it's only one. So y equal ax plus b. This would be a line. Y equal mx plus c or ax plus b. Now, if it's multiple, suppose we have x1 and x2. Suppose we have x1 and x2, right? And we have y. So y would be theta 1 x1 plus theta 2 x2 plus theta 0. So now let's denote this as x, this as y, and this as z according to the axis. So I'll explain what I'm trying to say. So suppose this is x. And okay, this is not x. Yeah, suppose this is y, this is x. So x cross y would be z. Z is in this direction, x is in this direction, y is in this direction. And we know the curl formula. So x cross y is z. So this is z. Now, suppose we have some theta 1 x1 plus theta 2 x2, and then some constant. So we have some kind of here. This is the target. And so therefore the curve would be something like this. A plane. This would be the curve, satisfying all these points. When you just project it down, it will be in terms of x and y, and it is like a 2D curve, which is a plane. This is a plane. So now we are trying to find the equation of this plane, which is the equation of y equal theta 1 x1 plus theta 2 x2 plus theta 0, which is our target right now. Okay, so now comes the loss. So we need to define losses first. So in simple linear regression, if you remember, if you have seen my video, and if you have even seen some other videos and you know what is simple linear regression, then you probably know that this is the line and these are the points This is the best fit line or the best fit curve for simple linear regression, and the differences are the losses. So the loss would something look like, the loss is the least squares loss function, which looks something like the sum of these differences squared. So this is the least squares loss function. So similarly, we would have something like this in multiple linear regression as well. So what would that look like? So that would be something like this. Suppose we have yi, which is the target. Y is the target, which is in our data set. And we are predicting y pred I, which is our predicted value. So we know that yi minus y predicted I, this is our loss. And we are using the least squares loss function. So y predicted I, so that you just now saw theta 1 x1 I plus theta 2 x2 I plus theta 0, right? So this is my y predicted value. Now there's an interesting way to write this. So we want to write it in the form of a vector so that we have simple equations to solve instead of this complicated equation with all the variables. So now theta, how do we represent theta? So theta would be n plus 1, right? Total number of thetas will be n plus 1. Because theta 0 to theta n for each of these x1 to xn feature. So theta matrix would be theta 0, theta 1 till theta n. 1 n plus 1 cross 1. This is our theta matrix. And our x matrix looks like this. I already said m cross n. Right? M being the number of data points and n being the number of features. So now our y would be m cross 1. So now if you can see carefully, so theta 0 has 1. This is very important. Try to understand this. This is the trick that you will use in most of the algorithms when you are trying to find the and you solve using the vector formula. So this is the 1 that we have. So let's say if we had x0, it would have been 1. So what we'll do is we'll add a column here of 1s. So then we'll make this. Let's make this. So this would be, these are the n features we have. Now we'll have another column of 1s. So this becomes plus 1. So this becomes n plus 1. So now you can see this is m cross 1, this is m cross n plus 1, this is n plus 1 cross 1. So we have a matrix multiplication here. So if we have theta transpose, what would theta transpose be like? 1 cross n plus 1. And then we'll have x. So we can write x in the form of like n plus 1 cross m as well. So that just depends on how you express x. Let's do that. Suppose we want to write x in the form of n plus 1 cross m. N plus 1 cross m. So this is our final x coordinates. So this would be n plus 1 cross m. Now we have 1 cross m, which is our y. So we can say y transpose, or we can represent it in the same way as x. So in that case, y would be 1 cross m. So it doesn't really matter when you're trying to solve. This is just the way we choose to express this formula, and we choose to relate y and x and theta. So this would be 1 cross m. So now you have this 1 cross m. So you have this equation, which is like very common, y equals theta transpose x. Now we want to use this. Till here, I think it's all clear. Now comes the loss. So we use j in order to represent our loss. So this is the I equal 1 to m, 1 upon 2m summation yi minus theta transpose xi square. So this is our least squares loss function. So I said this is our y predicted value, this is our y target value, and this is the way we represent the least squares function. So now we have the loss. So now we know what to do. We want to minimize this loss. So randomize, start, like initialize theta with some random values or 0, whatever you want, and then differentiate this loss function with respect to theta to get an equation and then equate it to 0 and then not equate it to 0, step by step, bring it closer to 0, like normally we do in gradient descent. Okay, so but I'll still explain it in case you're new here. Okay. Okay, so the next step is differentiating this with and equating it to 0. So what does this do? So suppose this is our curve. For simple linear regression, this is what the curve looks like. So here we are currently, this is our j theta. So this is our currently the loss function which we have after putting in 0 or any kind of random value. We are starting here. Now, since this is the slope, so we move along the slope slowly, and we try to reach this point, which is our target. Since what is this? This is the minimum loss. We want to reach this point. So what are we going to do? Simple, just differentiate this with respect to theta. I'll write the expression. Try it yourself as well and then try to match it. Okay, so one thing to clarify, this is for simple linear regression, but this can be extended to multiple linear regression as well. But trying to understand this by visually, this is very important. This is the curve, and the purpose is like the same. It's just extended to the multiple linear regression as well. The curve would not be exactly similar, but it would be same, almost similar. Okay, just one small tip here before we move on. Remember this, that when you are trying to solve a hard problem, it's always better to solve the easiest version of the problem and then step by step build it towards the hard problem. So here, multiple linear regression is relatively tougher compared to simple linear regression. But if you have learned simple linear regression already, and then multiple linear regression will be a piece of cake. It's very easy because it's just an extension with a little bit of vector formula and a little bit of more equations and a little bit more imagination and visualization. So if you have that out of the way, simple linear regression, then you know that multiple linear regression is nothing. So that is why do not try to like jump directly into hard topics. Try to break them down. If you have suppose a hard problem in interview or in exam, in any case, then try to find out the easiest version of the problem. Put some constraints. Try to think of in a perspective you can visualize and then solve it. And then you'll see that the harder problem becomes very easy and you have a path. Okay, enough pep talk. Let's continue. Let's finish this. Okay, so now we use the gradient descent formula, which is theta, t plus 1, t being the number, tth step, minus theta, not d, but delta, since we have multiple dimensions, d theta. So this is the gradient descent formula. This is our constant. We need a constant to determine the rate of convergence when we're trying to, as I said here, when we're trying to go from here to here. The rate of convergence is dependent on this learning rate. Now we are going to break this down. This is our, this is the toughest looking thing in this formula. Okay, so what is this and why is it creating problems in our life? Theta 0 upon d 0, d theta 0, d theta j1 upon d theta 2, d j theta n upon d theta n. This is our derivative. Now we are going to break this down. We are trying to find out. Let's try to find this out. So it's better not to do here. We won't be able to finish. So let's remove this. So now what we have is theta j d theta j. What would this look like? So if you remember, just I'm trying to write this here. Let's write it here. I'll remove this summation 1 upon 2m I equal 1 to m yi minus theta transpose xi square. This is what we are trying to differentiate with respect to theta j. So theta we know we have n thetas, n plus 1 thetas, theta 0 to theta n. M is the number of data points. Yi is our target. This is our predicted value. Okay. And the light falls here, but if you can see here, d theta j upon d theta j. D j theta j upon d theta j. Okay. So let's do that. Theta j. Y upon theta transpose xi square. This is 1 by 2m. is just a constant, so we can take that out and put it here. This is what we need currently. If it is not clear, 1/2m. Yeah, now it's clear. So we have d theta j, and then we have summation I equal 1 to m yi minus theta transpose xi square. Now let's differentiate. So this is partial differentiation. Remember this. We have here all the thetas from 0 to n. So this is partial differentiation. So if you feel a little shaky here, just remember that what happens in partial differentiation, we keep all the other terms constant except theta j, and we differentiate with respect to theta j. So this is just a simple funda of partial differentiation. Great. Now let's do that. And now this one. So minus, the others are all constants, so they'll all be 0. Only theta j will remain. So what is it? Minus theta j xi. So minus xi. That's it. Done. This is our differentiated value. If this xi, remember that when I was doing when I changed x, which was m cross n, into m cross n plus 1, I added a series of 1s. So just remember that in the case of theta 0, it will be 1, minus 1. That's it. That's it. Literally, you have done it. So now we are done. Just remember this 1/m summation I equal 1 to m yi minus theta transpose xi minus xi. This is the formula that you need to remember, and we are done. And this has to continue until, we know that this is continuing until, so this will continue until we have j theta minus, let's say theta plus 1 minus j theta t, like mod absolute difference. This is less than 10 to the power minus 6. So basically, what do I mean by this? Whenever this happens, the difference in the losses or the cost function, whatever you say it, whatever you call it, this is less than, like very less. It's not changing by much. So we know that we have reached our training is stable, and we have reached convergence, because it's not changing by much. It's not going to change now anymore. This is just a value we generally use for threshold. This can be any threshold that you want. This can be any threshold that you want. Okay, so now, so the curve looks like something like this. Here we are starting out. Here we have some value. Let's say we have some loss, and the loss is continuing to decrease. As you can see here, the losses are very small, and here it's almost negligible. So 10 to the power minus 6 is like a threshold that we generally use. You can use 10 to the power minus 9 if you want more precision, but that's up to you. Great. So now you understand multiple linear regression perfectly, and you can tackle any questions that come your way. I'll be discussing more interview problems soon. So stay tuned. Please subscribe. I hope this helps. Thank you.